Welcome to Fast Math Solutions on Maths with EJD. In this video, we'll be proving the generative function for Catalan numbers, which is used in combinatorics. Let's go for that. Um, the the Catalan number appears in various combinatorial contexts. Combinatorics deals with counting. Combinatorial contexts such as counting valid parentheses, rooted binary trees, and triangulations, triangulations of polygons. Okay, now the Catalan numbers can be defined recursively as C naught equals 1. That's the first term. And Cn plus 1 can now be summation from I equals 0 to n of Ci, then Cn minus I, okay, and n is greater than or equal to 0, like that. So now, what we want, our aim here, our aim is to prove that for the generating function, g of x equals summation from n equals 0 to infinity equals, summation from n equals 0 to infinity of Cn x raised to power n. That's the generating function. Our aim is to prove that for the generating function g of x equals that, um, we have, or I think it's better to write that apart to show how important that is. So our aim is to prove that for the generating function, uh, for the generating function, for the generating function g of x equals summation from n equals 0 to infinity Cn x raised to power n for a Catalan number, for Catalan numbers rather, for Catalan numbers, we can have g of x equals 1 plus x g of x squared. This is basically what we need to prove. Okay. Now to do this, so let's substitute. So we substitute the recursive definition. Substitute the recursive definition into the generating function. And that means we have Cn plus 1 equals summation from I equals 0 to n of Cn minus I, like that. We write Okay, better still, let me say, um, so using, so we substitute the recursive definition, which we already have up there, into the generating function, right? So we can say that we already know g of x is Cn h raised power n. So in that case, we just have to say that g of x is equal to c naught plus summation from n equals 0 to infinity of Cn plus 1 x raised power n plus 1. Because, we already have C naught apart up there. And don't forget that C naught is equal to 1 from what we have from the very beginning here. Okay. So that we now have g of x equals 1 plus summation from n equals 0 to infinity of Cn plus 1 x raised power n plus 1. So we have that. So we need to shift the index in the summation. So now we shift the index in the summation. In that case, we say let m be equal to n plus 1. So you see there's m. So n plus 1, let it become m. Then that implies that n now is equal to m minus 1. So anywhere you see n, it can be n minus 1. And now you can have x raised power n to be equal to x raised power m minus 1, which is the same thing as x raised power m all over x. Okay, so now rewriting the summation, we now have g of x equals 1 plus x raised to power summation from m minus 1, from m equals 1 to infinity rather, then cm x raised to power m minus 1. Now let's go back and compare the two. Okay, so here you have that one already. So, but in this case, n now is m minus 1. So since n is m minus 1, so m minus 1 equals 0. That means that m is equal to 1. So that takes over this place. And that's why you have m equals 1 down here, then to infinity, right? Then for n plus 1 is now m. So n plus 1 is taken over by this. And then n plus 1 up there. Yeah. So what's happening here? Okay, I think, in fact, let me just still, n plus 1 is m, right? So I think I would rather still just leave this one like this, first of all, and then, I'll leave this one so that it can be really clear. Okay, so I'll go step by step. So we have 1 plus this. Okay, so now that this is clear based on the shifting we have done, just by substituting, m for n plus 1 and then getting values for n and n plus 1 itself. So this is what we currently have. But now we can break this up, right? And we can have g of x equals 1 plus summation from m equals 1 to infinity of cm x raised by m minus 1 times x. Okay? So you see m doesn't have power over this x. So we can bring this x back. So we have g of x equals 1 plus x summation from m equals 1 to infinity of cm x raised by m minus 1. That's why we can have this x out here now. Now, you will notice now that if we simplify further, simplifying further, so more like, our, can we get back where we are coming from, right? So we have x up there, right? Like that. So if we simplify this further and do another substitution, okay. So if we simplify further, let me see. I want to clarify that very well. Simplify further. That's what we want to do next. So I just don't want to jump at it, and let's see what we so that it can be clearer. So from here now, we can shift this to conform with the original thing we are actually looking for. So, and that further simplification is going to give us the results we desire. Okay, so if we simplify further, we can actually get g of x equals 1 plus x, 1 plus x summation. So we reset this back to 0. Okay, we reset this back to 0, and then we now end up having n equals 0 to infinity, and then this will now be Cn x raised to power m, I mean Cn x raised to power n. So this is more like saying that so what we have done here should be something like this, that n is back to m minus 1, like what we had initially. Okay, so n is m minus 1. So instead of m minus 1, we have this. So in that case now, m itself, it's the substitution we made, n plus 1 is equal to m. Okay, so if n plus 1 is equal to m, that means that m equals 1 simply implies that n plus 1 is equal to 1. So n is equal to 1 minus 1. And that is why n there is going to be equal to 0. Okay. Yeah. So we have that. So that is what is happening around here. That's why we have this now. So simplifying further, we get g of x equals 1 plus x raised to power 1 plus x summation n equals 0, Cn x raised to power n. Now we can move on and say that therefore g of x is equal to 1 plus x, 1 plus x okay, 1 plus x g of x squared. 1 plus x. So this one now is now g of x all squared. G of x all squared. And that is exactly the proof we are looking for. So this part now is g of x squared. Yeah, and that's how much we have for this particular aspect to prove the Catalan number. All right, so that's it. I think I have one more video on Catalan number, just to prove another situation, another result related to this. So you don't want to miss out on that. So be sure to subscribe to this channel, hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are for you, and then let me know if there's a problem you'd like me to solve or a topic you'd like me to treat, and like and share so that more people can have access to this great, great, great content. Till I come your way again, keep doing maths right. Bye.